General classification rules in IPF assessment, standardizing IPF evaluation for consistent SIL determination. General classification rules provide the foundation for evaluating instrument protective functions consistently across different units, facilities, and operating contexts. These rules ensure that SCL assessments reflect not just technical factors, but also organizational tolerance for risk, regulatory expectations, and engineering best practices. By applying a structured classification framework, teams can compare risks objectively, justify protection levels transparently, and reduce variability in decision-making across projects. Key rules for IPF classification. Worst credible consequence governs. Always use the most severe credible outcome to determine the consequence level. The assessment must reflect the maximum potential impact, even if mitigated by alarms, procedures, or operator response. Likelihood reduction only with independent layers. Frequency, or likelihood, may only be reduced in SIL determination if independent, effective protection layers are in place, such as relief systems, alarms with documented operator action, or physical isolation. Control systems alone, e.g. DCS loops, do not count unless formally validated as independent. No dilution from multiple categories. If an IPF impacts more than one consequence domain, e.g. safety and environment, classification must reflect the most critical, not an average, impact. For example, if a single deviation poses both a minor environmental spill and potential for one fatality, the consequence must be treated as major. Bypass consideration is mandatory. An IPF's ability to be bypassed, manually or automatically, must be considered in classification. Easily bypassed or routinely disabled IPFs require higher diagnostic coverage, alarm management, or even reclassification. No credit for probabilistic operator response. Unless supported by data and formal procedures, operator actions cannot be assumed to reduce risk in real-time SEL determinations. Response times and human reliability should only be factored in where proven through formal assessment. Single failure sensitivity triggers higher classification. If a single failure in the IPF or associated equipment could result in an immediate or severe consequence, the function typically warrants SEL2 or higher, even if base risk is low. Shared functions must be evaluated separately. If one instrument or logic system serves multiple IPFs, e.g. a single shutdown valve used for both fire protection and overpressure control, each function must be individually classified based on its unique scenario and the most demanding SIL applied to the shared element. Degraded modes and diagnostic gaps must be considered. IPFs that operate under degraded conditions or that lack fault detection must be evaluated more conservatively. Example, if diagnostics cannot detect valve stiction, the dangerous undetected failure rate must reflect that exposure. Implementation in risk assessment and SIL tools. These rules are embedded in most corporate SIL tools, LOPA worksheets, and risk matrices. However, engineering teams must still apply judgment and context, ensuring that data inputs are validated and documented. Subjective judgments, e.g. what is credible, are peer-reviewed. Classification outcomes are repeatable across teams and projects. Conclusion: classification rules anchor functional safety. General classification rules prevent inconsistency, underestimation, or over-engineering in SIL assessments. They ensure that IPFs are evaluated not just on technical design, but also on operational behavior, exposure to failure, and real-world response limitations. By applying these rules rigorously, organizations can build safety systems that are effective, justifiable, and aligned with both risk and reality. Safe failure classification in IPF assessment, defining failures that do not jeopardize safety. Safe failure classification is a critical element in the reliability modeling of instrument protective functions, IPFs. While much of SIL determination focuses on dangerous failure modes, a complete and accurate analysis must also account for safe failures, those that do not prevent the IPF from performing its intended function or, in some cases, even initiate a conservative, safe response. Understanding the distinction between safe and dangerous failures enables calculation of key reliability metrics, such as the safe failure fraction, SFF, and facilitates selection of appropriate system architectures, e.g. 1U1, 1U2. These classifications are essential inputs into SIL verification and hardware fault tolerance, HFT, decisions. Safe failure mode categories. Each IPF component, sensors, logic solvers, and final elements, is evaluated for failure behavior using the following standardized categories. Safe detected, SD, failures that do not pose a risk and are immediately identified by internal diagnostics. Example, a transmitter experiencing a sensor error that triggers a diagnostic fault, allowing timely replacement. Safe undetected, SU, failures that do not impair safety performance but are not immediately identified without manual intervention or periodic testing. Example, degradation in a pressure transfer transmitter that remains within specification but is trending toward failure. These failure modes, while not threatening to process safety, still impact system availability and maintenance strategies. Their accurate classification supports a holistic picture of system behavior. Implications for safe failure fraction SFF. Safe failures contribute positively to the SFF, a metric defined as SFF equals safe detected plus safe undetected, dangerous detected, total failures. A higher SFF reduces the required hardware fault tolerance for a given SIL. For example, an SFF 90% may allow a 101 architecture for SIL 2. An SFF between 60 to 90% typically requires at least a 102 architecture for SIL 2 or 3. An SFF 60% demands higher redundancy or frequent proof testing. Accurately estimating SFF through failure rate data, third-party certifications, e.g. IEC 61508, and field experience is essential to avoid underestimating required system robustness. Design and maintenance considerations. Safe failure classifications also inform design and operational practices. Diagnostics implementation. Embedding self-checks in transmitters, logic solvers, and final elements increases the proportion of failures that are detected, i.e., SD, thus improving SFF. Proof test coverage. Periodic testing helps reveal SU failures, reducing exposure and refining system performance data. Spare parts and repair planning. SU failures may not require immediate repair, but should trigger replacement before escalation to dangerous states. Maintenance efficiency. Systems with high proportions of SD and SU failures are easier to manage and less prone to unexpected outages or safety function compromise. Conclusion: safe failures are an integral part of SIL integrity. Safe failure classification ensures that the reliability of IPFs is not overstated or understated. While dangerous failures determine functional safety risk, safe failures influence design efficiency, maintenance planning, and diagnostic requirements. By correctly identifying and leveraging SD and SU failures, organizations can optimize IPF performance, meet SIL targets with leaner architectures, and enhance operational confidence without compromising safety. Documentation in IPF lifecycle management, enabling traceability, verification, and compliance. Comprehensive documentation is the backbone of any effective instrument protective function IPF strategy. From initial risk identification through commissioning and into long-term operation, documentation provides the traceable evidence that an IPF is designed, implemented, maintained, and tested in accordance with its required safety integrity level. More than a regulatory formality, IPF documentation enables consistent decision-making, supports audits, simplifies future modifications, and ensures that all stakeholders, from engineering to operations, share a unified understanding of the safety function. Core documentation requirements. Each IPF must be supported by a complete and organized documentation set. Key elements include: Safety Requirement Specification defines the IPF's purpose, SIL target, trip logic, process conditions, allowable response time, test intervals, and diagnostic requirements. Acts as the governing document for design, procurement, and validation. SIL determination records details the methodology used to assign the required SIL, e.g. LOPA, risk matrix, including assumptions, consequence classification, risk tolerability criteria, and protection layer credits. Must be signed off by a multidisciplinary team and retained for traceability. Design, basis, and hardware selection documents the selection of certified or proven in use components, including failure rate data, diagnostics, and environmental suitability. Includes architectural justification, e.g. 102 versus 2003, response time calculations, and process safety time validation. Verification and validation reports demonstrates that the IPF, as implemented, meets the required SIL. Includes PFDAV calculations, proof test coverage analysis, and simulation or factory acceptance test results. Loop and logic diagrams shows sensor to logic to final element connections, signal routing, and any voting configurations. Must reflect exact field installation, including redundancy and bypass pathways. Cause and effect matrix maps initiating events to IPF responses, including logic solver behavior, alarm sequencing, and fallback modes. Supports both commissioning validation and operator training. Documentation. Beyond design, ongoing IPF performance must be documented to maintain integrity over time. Proof test records includes test dates, results, discovered failures, and any corrective actions. Should be linked to the original SIL calculations to monitor actual failure rates. Bypass and override logs captures all periods when the IPF was intentionally or unintentionally disabled. Ensures compensatory measures were applied and reviewed. Change management records documents all hardware, software, logic, or configuration changes to the IPF, including revalidation and stakeholder approval. Incident and demand logs records real-world IPF activations, e.g. trips or shutdowns, along with root cause analysis and outcome evaluation. Helps validate design assumptions and support continuous improvement. Format, ownership, and accessibility. Documentation must be version-controlled, regularly reviewed, and accessible to engineering, operations, and safety teams. Digital platforms are recommended for traceability, with automated reminders for proof test intervals, change reviews, or SRS revalidation. All documents should have clear ownership, typically with safety or instrumentation leads, and align with corporate functional safety procedures. Conclusion: documentation anchors safety and accountability. Effective documentation transforms an IPF from a technical implementation into a managed, auditable safety system. It ensures that safety integrity is not only designed into the system, but sustained over time. By maintaining complete, clear, and current records, organizations strengthen both compliance and confidence, while enabling proactive performance management of their most critical protective functions. Introduction to IPF design and implementation. Establishing a framework for reliable protection. Instrument protective functions, IPFs, are engineered safeguards designed to detect abnormal process conditions and take automatic action to prevent escalation to hazardous events. As critical layers in a facility's overall risk reduction strategy, IPFs must operate with high reliability, precision, and predictability, especially under stress conditions where other systems may have already failed or been bypassed. The implementation of an IPF is not a one-dimensional activity. It is a lifecycle-driven process that integrates process engineering, functional safety, instrumentation, control systems, and operations. From concept to commissioning, and throughout routine maintenance and testing, every phase must align with the function's required safety integrity level SIL, risk reduction objective, and operational context. Why IPFs matter. In modern process industries, IPFs serve as the final line of defense between a process deviation and its potentially severe consequences, ranging from loss of containment and equipment damage to environmental violations and human harm. Their performance must be guaranteed not just in theory, but in real-world conditions, including startup, shutdown, and transition modes, instrument degradation or drift, human error such as miscalibration or bypass, adverse environmental or power supply conditions. A well-designed IPF accounts for these realities and ensures that it delivers timely, decisive action when called upon. Scope of implementation. This guidance outlines the principles, expectations, and engineering practices associated with IPF implementation. Topics covered include specification of the function based on risk analysis outcomes, selection and configuration of instrumentation and logic hardware, design of fail-safe architectures and response times within process safety time, integration with control systems, alarms, and operator interfaces, commissioning, proof testing, and maintenance strategies, lifecycle documentation, performance monitoring, and change management. The goal is not just to achieve compliance with safety standards, but to embed protection that is effective, auditable, and sustainable across decades of operation. IPFs as dynamic systems. IPFs are not static, one-time installations. They must evolve with process changes, updated risk evaluations, and technological advancements. As such, their implementation must be holistic, considering the entire detection, logic, and actuation chain. Risk-informed, aligned with consequence severity and tolerable risk thresholds. Testable and verifiable, capable of demonstrating functional integrity over time. Operationally practical, designed to support, not hinder, plant operations and maintenance. Conclusion: a foundation for functional safety. This introduction sets the stage for a structured and disciplined approach to IPF implementation. It recognizes that reliable protection is not a function of components alone, but of clear intent, sound engineering, and rigorous lifecycle management. Through proper design, validation, and documentation, IPFs can fulfill their role as dependable safety barriers, protecting people, assets, and the environment when it matters most. Assigning a SIL to the initiator, logic solver, and final element. Ensuring consistent integrity across the entire IPF loop. A Safety Integrity Level SIL is not just applied to the instrument protective function IPF as a whole. It must be achieved by each component that makes up the IPF loop: the initiator, sensor, the logic solver, decision-making unit, and the final element, actuator or control device. Assigning and validating SIL at the component level ensures that the complete function delivers the required risk reduction with no weak links in the chain. Each part of the loop contributes to the overall reliability of the safety function. A failure in any one of these can render the IPF ineffective, even if the other components perform correctly. As such, SIL requirements must be applied consistently and systematically across all elements. Initiator, sensor, or detector. The initiator is responsible for detecting the abnormal condition that triggers the protective function. It could be a pressure transmitter, temperature sensor, level switch, flame detector, or gas analyzer, depending on the nature of the hazard. Key considerations for SIL assignment to the initiator include response time must be fast enough to capture process excursions within the process safety time. Reliability. Failure rates must be known and verified, preferably through certification or proven in use data. Diagnostics. Sensors with built-in self-checks and signal validation contribute to higher safe failure fractions. Environmental robustness. The sensor must maintain integrity in expected process and ambient conditions, temperature, vibration, EMC, etc. Redundancy, e.g. 2003 voting, may be used to improve reliability where individual sensor performance is insufficient. Logic solver, safety system controller. The logic solver interprets the input signal from the initiator and determines whether to activate the final element. This could be a dedicated safety PLC, hardwired relay logic, or certified logic card within a safety instrumented system, SIS. SIL assignment to the logic solver is based on diagnostic coverage, ability to detect internal faults and ensure correct processing of signals. System architecture, use of redundant CPUs, watchdog timers, and safe state behavior. Execution time, must process inputs and deliver outputs well within the available process safety time. Certification, the logic solver should meet IEC 61508/61511 standards for the assigned SIL, including software lifecycle and cybersecurity considerations. Interfacing with the basic process control system BPCS must be designed to preserve independence where required. Final element, actuator, valve, or breaker. The final element performs the actual protective action, such as shutting off flow, venting pressure, or isolating energy. It is often the most failure-prone part of the IPF loop due to mechanical wear, fouling, or actuation delays. SIL requirements for the final element include actuation reliability, must function on demand with documented failure rates and response consistency. Partial stroke testing, where full testing is impractical, automated partial testing helps detect degradation. Fail-safe design, must move to a safe state on loss of signal or power. Valve and actuator integrity, position feedback, solenoid diagnostics, and stroke time monitoring enhance reliability. Where risk is high, redundancy or diverse actuation paths may be necessary to meet SIL targets. Integrated SIL achievement. The required SIL for the IPF is only met if all three components, initiator, logic solver, and final element, individually meet or exceed the same SIL level. A weak link in any one part degrades the entire function. During CL verification, each component's contribution to the probability of failure on demand, PFDAVG, must be calculated or validated, and the total must fall within the allowable limit for the assigned SIL. Conclusion. SIL must be delivered as a complete system. Assigning us is not a label, it is a performance expectation distributed across the full IPF architecture. By evaluating the initiator, logic solver, and final element individually and collectively, engineers can ensure the IPF performs reliably under all operating conditions. This approach ensures the protective function operates not only in theory, but in every real-world demand, safeguarding people, assets, and the environment as intended.